glad to see everyone here. What an enthusiastic audience. So I'm going to be talking to you about something that I'm very interested in personally and also professionally from a research perspective. I think actually in neuroscience it has the potential to change everything. And so let's jump right in. So the problem that I have been grappling with, it's a good idea when you start working in a research area to start with the end in mind. What is the problem that I want to solve? That's sort of the reason that you get up in the morning every day and you go to work and you do your research. And the problem that I wanted to solve was this one, which is how are we going to age? For each one of us, the trajectory will be different. For about half of the people in this room, you'll be fine. And about half of the people in this room, from a neurological standpoint, you won't be. And so as someone who works very closely with patients, I've seen dementia up close. It's heartbreaking. It's a very, very hard thing to face. And at the same time that we're taking care of our bodies, from our perspective, we also have to think about quality of life. And to have a very strong body and a mind that can't appreciate what that strong body has to offer is problematic. So if we think about the process of aging, and we think of it as a trajectory, we can also notice that dementia is not something that behaves like a cliff. It's not like you're fine, 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 and then all of a sudden you're not. It's really a slow and steady progression. And so if you look over here, you can see that there's early brain changes, subtle decline in thinking, memory changes. Eventually you can't function, and eventually you become kind of vegetative. And the question is, from my perspective, neurobiologically, even though we want to start with the end in mind and think about dementia as the problem we want to solve, almost all of the research has really focused on working with patients with dementia and trying to reverse dementia. And at this point in my career, I can say that won't work. That's not a treatment approach that's going to work. The only chance we have is to catch it at stage 1 and fix it at stage 1. So when we think about our imaging tools that we have diagnostically, the problem is that the tools that we might be able to use to catch it very early on also happen to be very invasive, right? So looking at the cerebral spinal fluid or amyloid imaging is a pretty invasive method. It's not something you're likely to do in a doctor's office. So what I've been working on is, first of all, trying to figure out a way to see it, because if you can't measure it, you don't know if you fixed it or not. Remember, I'm looking at people who are pre-symptomatic. And second of all, once I can see it, once there's a signature for me to latch onto, can I then fix it? Is there a treatment strategy? So it's a two-pronged approach. Now, the approach that we're taking here in thinking about dementia as a neurodegenerative disease and trying to understand what happens between stages 1 and 5 is helped by the fact that if you look at a certain type of imaging known as FDG PET, or this is looking at basically radiolabeled glucose in the brain, how it's being taken up, and you look at these images over here, this is what Alzheimer's disease looks like. And what's happening is that the glucose is really not being used. Okay? All of those black areas are areas of neurons that are not taking up glucose. Cognitive impairment is less, and normal glucose is being used throughout the brain. So we might start from that point and say, hey, brain aging might have something to do with how the brain uses glucose. Okay? And that's a great place to start. So if we think about how the rest of the body uses glucose, we understand that there are basically two pathways. So the body has a saving mode, and it has a spending mode. Okay? And what we do is, when we have access to food, we save, and then when we don't have access to food and our bodies need fuel, we spend, right? And so the saving mode is the one given by the purple lines. And when you eat a cookie, let's say, which no one in this room I'm sure would ever do, you have blood sugar spike, which then causes the pancreas to release insulin. That allows the blood sugar from the cookie to get into your cells and feed them. And then that lowers the blood sugar because it's now being used. The other pathway is the spending mode, which is that when your blood sugar is running low, let's say you've been without eating for a while, your pancreas will send a different signal, an opposite signal, glucagon, which will gather stored glucose, which has been stored as glycogen in the liver, and release it into the bloodstream so that your cells can use it. So we can think of this, as I said, as a spending and saving mode. They can't happen at the same time. Unlike in a bank, where you could deposit money and take it out at the same time, your body can't do both at the same time. It has to be in one mode or the other. So it has short-term storage. So if you eat that cookie and it's in your bloodstream, and then you go run after a bus, the glucose in your bloodstream is going to get used up right away to feed your muscles, right? And then you run. If you are not running after a bus, then if you're not using it up, your body stores it in the short term. And we can think of this as, instead of having coins in your pocket, which is your blood glucose, instead you're going to put it in a wallet. You might put it in a wallet for a little bit longer storage. You can still access it pretty easily, but it's put away. Now, if you fill up your wallet after a certain point, you're going to deposit it in longer-term storage, which in this case is the bank. Okay? And taking that analogy further, that is really fat. Okay? So this is kind of an ingenious method that the body uses to make sure that when you have access to fuel, and if you're not using it right away, you store it for later so that when you need it, you can access it. And that's why fat is actually a very adaptive thing to have on your body. Now, if we think about what insulin resistance is, insulin resistance is the problem, is the lack of being able to actually spend. It's an inability to actually access the cells with the glucose. So I think somebody has my key. Somebody was supposed to hand me a key. Okay, thank you. So this is my room key, right? And the way a room key works is that you want to get into your room and you put it next to the door, and then the door opens, right? So your cells work that way. You have your glucose. The glucose triggers insulin, which is a hormone. And then the insulin, I don't know if you can see over there where that one is, the insulin locks into the insulin receptor. And that's kind of like putting my key next to the door. So when I use my key, I can then open up the door. If I don't use my key, it won't open up. And so if you are insulin sensitive, then the insulin is behaving properly and is being read like a key, which is allowing the glucose to get into the cells. When you're insulin resistant, it's like you're putting your key next to the door and it's not reading it. The card reader is not working, so you can't actually open the door. And as a result, what's happening is that the glucose can't be spent, so it has to be stored. It has to be saved. And that's why people, when they become insulin resistant, they actually wind up putting on a lot of weight because they can only put on fat. They're not in a position to actually make use of their stored resources. So one of the things that people often misunderstand is they look at someone who's insulin resistant, and often people who are insulin resistant are heavy, they're overweight. And they also see that this person is eating a lot, right? And they say, oh, well, clearly they're gluttonous, they can't control themselves, they're just eating and eating and eating, and they should just stop eating. But what they don't understand is that what's happening is the reason they're eating is because their cells are starving. And so what's happening is that they're eating, and that glucose is getting stored as fat, but the cells aren't able to make use of it. So they are starving, and that's why they continue to eat. So they're not fat because they're eating because they're fat. And so I kind of liken this to, the teenager who's not listening. What happens with the body is that it's got the card reader and it's saying, hey, let me in, let me in, let me in. The door's not opening, and so the pancreas produces more and more and more insulin trying to get in. But the card reader isn't working. So it doesn't matter how loudly you shout, the door isn't opening and your teenager is not responding. So this is how it works in the body. Now, the part of the body that I'm particularly interested in is the brain, right? So let's think about here the GLUT3, GLUT4 transport, which is the mechanism, again, that we're going to use to open that door. And until very recently, it was assumed that the brain didn't use this mechanism, that the brain actually did not make use of insulin. But it turns out that's actually incorrect. There, in fact, are insulin receptors in the brain, and we know that for a fact. And in fact, if you use that same FDG PET to look at glucose uptake in the brain, you can see that in people who are insulin resistant, actually take up less glucose in the brain. Okay, so the process of being insulin resistant, where your cells can't make use of glucose, actually is existing in the brain, and that is actually very big news. There are a lot of medical textbooks that don't have that information yet. Now, if you're me, you look at this and you see that these patterns are pretty intriguing, because this might look like lots of blobs on the brain, but their position is actually very similar, and even I would say identical to the pattern that you see in PTSD of hypometabolism. And that's relevant because both depression, stress, and also sleep deprivation, these are all different types of stressors, produce a kind of toxicity to the brain that has a very particular pattern. It's really, the neurotoxicity is specific to where the GLUT4 transporters are in the brain, which is the prefrontal cortex and hippocampus. And those are the areas that disproportionately start to suffer, and the neurons eventually start to die. So when you have people coming back from Iraq, for example, with PTSD, what's happening is that they're often reporting not just emotional symptoms, but cognitive ones. They're having trouble concentrating and thinking clearly, because those parts of the brain that make use of insulin are actually not working properly. And here's exactly what's happening. So if you look at the normal state, you see that here's a dendrite. So the way that neurons connect to one another and communicate with one another is through these synapses. And the synapses connect to each other through dendrites, right? So those little knobs are actually where they connect. Those are the connections. When someone is stressed or depressed or sleep deprived, the neurons actually become insulin resistant. And what happens is that there's a loss then of what's known as this dendritic arborization. You can see those little knobs start to fall off. And what that means is that the neurons then can't connect to one another, because that's the place where they connect. So interestingly enough, if you feed someone cortisol, which is the stress hormone, you see that actually there's this structural change in the brain where the insulin resistance actually causes the dendrites to start becoming spindly and die. If you give someone then an antidepressant, they regrow, right? So you see there's a very clear correlation, causally. So this was a rat experiment that was done where you have on the top cortisol-induced hippocampal damage. So this is a part of the brain that is associated with memory, right? So when you're stressed, you probably notice that you lose things. You forget your keys, you forget things, right? And that's because the part of the brain that is disproportionately affected is the hippocampus, which is responsible for memory. And you can see here that it started to become degraded, right? The brain is starting to degrade. But if, in fact, you feed that same brain then exogenous ketones, the neurons plump right up, because now they have a fuel source. So even though the neurons are insulin resistant from the stress, the ketones are able to bypass that insulin resistance and still feed the neuron. So we can think about my hotel room, which has a card reader, right? It's not working, I'm getting really frustrated because I'm trying to get into the room, it's not working. But it turns out that there's a cat roaming the hallways, and there happens to be a cat flap underneath. The cat just walks right in, because the cat is not making use of the card reader. He has a different path for getting in. And ketones don't make use of the card reader. They don't make use of GLUT4. They don't need to get in the same way. They can walk right in. So even when neurons are insulin resistant, it seems that ketones still can feed the brain. Yeah, that's big news. So that suggests actually a kind of important mechanism that we can then look at. So we have a way to make the neurons insulin resistant, and then we also have a way to feed them, refeed them through exogenous ketones. So I told you that what the insulin resistance is doing is it's actually making it harder for those neurons to connect to one another. When they don't connect to one another, all of those circuits that allow you to think clearly, so the circuits that are responsible for spatial navigation if you're trying to drive through a new town, or the circuits that are responsible for, figuring out your account balance in the bank, or anything you do requires connections between different parts of the brain. If, in fact, those connections start to break down, then structurally your brain is going to start remodeling. And what will happen is that the networks that are necessary in order to do the computational processes of thinking are not going to be able to be maintained, because those connections require energy and the brain is lacking in energy, right? And so we can think about this connection, these networks changing, as a sort of dynamic connectivity. So if we look at the age span, the lifespan, and we look at individuals, so this is 636 individuals, but we have many different data sets. At this point, we have about 30,000 individuals. We can look at the age of 18 to 88, and what we see is that there's a very marked destabilization that occurs with age. But it really picks up steam around the age of 47. So around 47, something happens. And for those of you who are sort of in that age range and noticing that, you know what, I don't remember names sometimes, you're not imagining it. And that becomes sort of precipitously destabilizing until about the age of 72. At that point, it's bad, but it stays bad. You see there's quite a bit of variation, though, too, because there are some people who do well and some people who don't do well. What we've also found is that type 2 diabetes, or insulin resistance, accelerates this process of aging. So what we find is that in people who do not have insulin resistance, there's a big difference in the stability of their brain networks between the younger people and the older people. But for people who are insulin resistant, their brains look indistinguishable from those of people who are older than they are. And so what it seems to be doing is taking a process that happens to most of us as we age, and it accelerates it. And the reason why, again, is that the process of insulin resistance robs the brain of energy. And eventually what happens is that those neurons are not able to connect to one another as efficiently, and eventually they die, which seems to be that process of hypometabolism I showed you on the first slide. So if we take younger people, okay, so that was the really depressing slide, the last one. Now I don't like to create problems without trying to solve them. So here we took individuals, young people, before they hit that curve. So 20 to 38. And we put them on 1 week of a diet. On 1 week, they followed a high glycemic diet, your typical food pyramid. On the other week, we put them on a ketogenic diet. I just want to point out 2 facts. First of all, these are young people. Okay? These are not middle-aged or old people. These are not type 2 diabetics. They're not insulin resistant. And they were on the diet for a week. Okay? You wouldn't think that people would see dramatic changes in anything in a week. But in fact, their brain networks stabilized on a ketogenic diet. And the mechanism for that, we think, is that ketones are a more efficient energy source. They produce about 25% more ATP per unit oxygen. And so even for these people who are not, hypometabolic in their brains, the added energy allowed them to sustain their networks for longer. Now, what we want to do here is say, okay, what about exogenous ketones, which is something that everybody here cares deeply about. So here we have an example of an individual, but this was true also for the group, where we put people on a high glycemic index diet with and without the exogenous ketones. Because face it, most people are not changing their diets when they go on the ketones. They should, ideally. But what happens if they don't? Worst case scenario. What we found is that even if they don't change their diets, the ketones still stabilize their networks. Okay? So what are we learning here? First of all, a ketogenic diet stabilizes brain networks. That's a good thing. It means you can think more clearly. But even if you're not on a ketogenic diet, taking exogenous ketones produces the same effect. By the way, we did not see, we had also different conditions where we had people on a ketogenic diet, taking ketones, not taking ketones. It didn't look like taking more ketones was better than taking fewer ketones. Once you're burning ketones, your brain has what it needs, and giving it more doesn't improve it further or make it worse. It's sort of a threshold effect. So again, the point I want to make from this slide is for healthy, normal individuals, following a ketogenic diet and taking exogenous ketones from the brain's perspective are identical. Okay? And I just said I think it's because for healthy individuals, they're getting more energy because of the 25% more ATP per unit oxygen, but we measured it, And in fact, here we're testing people under different conditions, just hanging out in the scanner, doing absolutely nothing. And then we had people do a motor task, essentially like driving a car. And then we had them do spatial navigation, where they actually had to maneuver their car through some unfamiliar territory and find their way back. And we had them do it for a long time so that they started to get fatigued. And pretty reliably, we see that glucose and ketones behave very differently, with ketones producing a lot more energy for the brain than glucose. So those T-shirts that say ketones greater than glucose, this is literally true. I've measured it. But I want to point out something else here, which is kind of interesting and intriguing. If you look at the red and the blue lines, we had people doing an overnight fast for one of the conditions. And what you'll see is that the ketogenic condition and the fasting condition look the same. So why is that? Well, the reason for that is that actually when people fast overnight, and we're not talking about fasting for a day, we're talking about sleeping at night. You're probably used to thinking that when someone goes into ketosis, it takes, let's say they're not exercising, they're just being, it's going to take them about 30 hours of not eating in order to get into ketosis. But the interesting thing that makes the brain different than the rest of the body is that for the rest of the body, it stores glycogen in the liver. But the brain stores glycogen in glia, in microglia, in the brain, local. And the glycogen that's stored in the glia is of a very small quantity compared to the liver. And that means that people run out of glycogen much faster. So when you sleep, the only reason you can sleep a full night is because your body goes into ketosis. So even if you're measuring someone's blood, right? You're taking a blood measurement. And the blood measurement or the urine measurement doesn't show that someone's in ketosis. Their brain already has switched to burning ketones if you're a healthy, normal person. So again, for a healthy, normal person, if what you want to do is to protect your brain from the processes of aging, you should get your brain running on ketones, and there are many ways to do that. You can do it through taking ketones, you can do it through following a ketogenic diet, you can do it through exercising. All of those are producing essentially the same pathway. And in fact, researchers have found that caloric restriction improves memory in elderly humans, and all of those good lifestyle changes that everyone should participate in do in fact, from a research perspective, work. But not if you're insulin resistant. So if you look at these results, here we're going to show data a little bit differently. This is a different study that we did where we had people come in fasting and then they had a glucose bolus, or they, on a different day, were fasting and they took a ketone bolus. And now we're going to subtract glucose minus fasting, ketones minus fasting. So what we're going to do is look at the difference between the glucose and ketone conditions, which in this case they're drinking something, in both cases, versus what they came in looking like, fasting. And you can see for a healthy, normal individual who is not insulin resistant, if the blue line is the baseline fasting condition, what you see is that the ketone ester, so the exogenous ketones, basically look exactly the same as when they are fasting, right? That's why they're centered around the 0 line. If you have 3 minus 3, you get 0, right? And it's the glucose that's destabilizing the networks. But if you take someone who is insulin resistant, so here we have someone age 47 who's starting to become insulin resistant. They're already at that bad part of the curve. And what you see here is that their glucose bolus and fasting look the same. It's the ketones that are pushing you way down and making you stabilize the networks. So this is actually extraordinary, because what it means is for healthy individuals, the fasting in ketogenic conditions, meaning the endogenous ketones that we burn from our own bodies when we're burning our own body fat, and the exogenous ketones that we take, in those powders you sell, do exactly the same thing. They have the same beneficial results. But for someone who's insulin resistant, they don't. For someone who's insulin resistant, fasting actually does not put them in a ketogenic state. And it's only the ketones that are able to bypass the insulin resistance and stabilize the network. So let's try to figure out why. Maybe some of you have already figured this out. So obviously, we evolved within a hunter-gatherer environment where we have periods of feasting and periods of famine, right? And so our body transitions very nicely from storing and spending, right? Saving and spending. But as I said earlier, glucagon and insulin, the two hormones responsible for each of these processes, they can't be on at the same time. You can't both be storing and spending simultaneously. For someone who is insulin resistant, the high blood glucose levels are triggering insulin. Insulin is trying to lower the blood glucose levels, but because those cells are not letting the glucose in, it produces more and more and more insulin in order to lower the glucose levels, but it's not working. And so people who are insulin resistant are walking around with chronically elevated insulin. As a result, because they have high insulin levels, their glucagon levels cannot turn on. They can't raise. And without glucagon, there is no mechanism to actually go into ketosis naturally. You can't access that stored energy from your fat or from your food without glucagon, and glucagon can't turn on as long as your insulin levels are high. So from that perspective, exogenous ketones have a very unique role to play, because during that vulnerable time when insulin-resistant individuals are trying to make those lifestyle changes that ultimately would get rid of their insulin resistance, you're going to find, if you know people who are insulin resistant, that that transition is very, very hard. And it's super hard, not because they lack willpower, not because they lack initiative or dedication. It's because their bodies are not working properly and they can't access the energy from any other pathway. And from that perspective, the exogenous ketones can provide this buffer that allows the cells to receive fuel until they can change their diets and start exercising and all of those things. But if you start exercising a storm and you don't have access to glucose, and also you don't have access to glycogen, and also you don't have access to fat, you don't have access to energy, which means it's not really going to be sustainable very long. And again, that's where the exogenous ketones play a very vital and unique role. Now, if we think about what the implications are, though, of not being able to fast, not being able to go without food because you have no way to access your reserves, one of the real problems with that is with sleep, because sleep is a period of time during which we're going to run out of fuel. As I said, your microglia are going to run out of glycogen while you're sleeping. And as a result, people who are insulin resistant don't sleep very well. What happens is that they go through the first few stages of sleep, but then they run out of fuel. And when they run out of fuel, something very important happens, which is this. So one of the things that happens when you eat, when your cells consume any sort of energy, is that they produce waste. And therefore, the body has a system of waste management, right? Part of that is in pruning, in figuring out what you're going to keep and what you're not going to keep. So if you were only buying things, but you were never throwing things away, your house would look kind of like that, right? So part of having a well-organized household is being able to choose, what am I keeping, what am I not keeping? In the brain, this is known as synaptic pruning. During the day, you're having all sorts of experiences, your brain is producing all sorts of synaptic connections. At night, it's choosing, which ones do I keep and strengthen, which ones do I get rid of and prune. It's sort of like a well-tended garden. As you can imagine, your household is not going to function very well if you never get rid of stuff. When you look at a map of, let's say, the subway, or of the connectome in the brain, there are certain organizing principles. You don't have everything connected to everything. Otherwise, it doesn't work. If you had a subway system where every stop was connected to every stop, it would be utterly chaotic. Instead, there's some structure that allows the most important connections to exist and other connections not to exist. And so you see this process. So at birth, we have very few connections. At 6 years, we're producing lots and lots and lots of connections. But you don't reach your cognitive peak at 6. What happens during the teenage years is you stop making so many connections, and instead you start organizing them. You figure out which are the ones that are meant to keep, and you strengthen them, and there's some that have to be pruned. And therefore, what happens in the teenage years is you start organizing your brain. Okay? You keep what's necessary and get rid of what's not necessary. In someone who's insulin resistant and is missing those critical late stages of sleep, they don't go through that synaptic pruning, because that synaptic pruning is occurring during the end stages of sleep. The second process, of course, has to do with waste in a more basic level. Your cells are producing poop, unfortunately. And it has to be gotten rid of, and so we have a lymphatic system in the rest of the body, and in the brain it's called the glymphatic system. And so part of that waste are these proteins, the tau proteins, the beta amyloid proteins, that you've probably heard of in the context of Alzheimer's. So if you are non-insulin resistant, you are producing beta amyloid plaque, trust me. Every single time you eat a brownie, you are producing beta amyloid plaque, because that is a metabolic waste product of glucose metabolism. But your glymphatic system is cleaning it up at night during those last stages of sleep. If you are not sleeping properly, if you are running out of energy before you get to complete that cleaning process, that cleaning cycle, it's sort of like you're running your dishwasher cycle, but you never let the cycle finish. then what will happen is you will accumulate a lot of this waste. If you are consuming ketones as opposed to glucose, you actually produce less of this metabolic waste because ketones are a cleaner fuel source to begin with, right? So you see here, with the normal condition and the ketogenic condition, the brain looks cleaner. It hasn't accumulated as much waste. But in fact, also, when you have the waste, the ketones allow the brain to clean it up more completely. So you're producing less waste, and also of the waste that you create, you clean it up more effectively. So in terms of my take-home messages, with age, but faster with a high-sugar diet, neurons can become insulin-resistant, and when they do, they run out of energy. So essentially what happens is that initially they become metabolically stressed, eventually they starve and die. Those so-called senior moments are those first warning signs that your neurons are becoming metabolically stressed, and eventually those neurons will die, and at that point you start to see real cognitive impairment. And so that progression of mild cognitive impairment to severe cognitive impairment is really just more and more neurons failing and dying. Ketones can bypass neuronal insulin resistance, restoring neurons' energy source and therefore communication through the brain, which is great news. Ketosis normally can be achieved in 3 ways: fasting, exercise, and exogenous ketones. All 3 protect the brain equally well if you are healthy. If you are insulin resistant, however, only exogenous ketones can reach the brain because insulin resistance will increase your insulin levels and have them be chronically raised, which means that even if you're following a ketogenic diet, even if you are exercising a lot, you're not able to access your own fat reserves. Stress and sleep deprivation cause brain-specific insulin resistance. And in the brain, glycogen is stored in glia, not liver, so it runs out faster than the rest of the body, between 5 to 10 hours. If you can't naturally produce ketones during your sleep, you're going to run out of energy. You don't complete your sleep cycle, which means that you wake up tired, even though you have been sleeping. You haven't been sleeping effectively. You haven't cleaned out your gunk. That actually produces additional stress, which then makes your neurons even further insulin resistant. So it's a kind of a vicious cycle that becomes worse and worse and worse. And here again, exogenous ketones seem like a way that in principle we might be able to break that vicious cycle by being able to feed the neurons, then they can complete their sleep cycles and eventually recover. Okay, thank you very much.